Bismillah Rahman Rahim. So we were discussing the coding simulation of a wind, solar, hybrid renewable energy system connected to the grid. With respect to load management strategy, in economic analysis file or in the fitness function, we were discussing an economic cost function that is taking in solar, the size of the solar, the number of wind turbines, grid purchase and sold energy as input, and in return it will give us annualized cost, wind cost, solar cost, grid cost and inverter cost. So here are some cost parameters. It's capital cost of the wind plant per wind plant or per 10 kilowatt, because the size of each wind turbine is 10 kilowatt. It's the replacement cost, and here it is operation and maintenance cost. Similarly for solar, it is capital cost is 650 and OM cost is operation and maintenance cost is 4. Similarly, this is for inverter per kilowatt $300, and this is the replacement cost and OM cost. Here is the life of each component, PV, wind, inverter, whatever, and for each component we are calculating its cost. So this section is for wind. So in the wind calculation, what we have to calculate: the overall capital cost of an wind plant, the overall cost of the operation and maintenance cost of an wind plant, and what is the replacement cost, what is the salvage cost, and what is the total cost by summing all these OM cost, capital cost, salvage cost and replacement cost. So first of all, to calculate the total wind capital cost, so we have to multiply the size of the wind turbine multiplied by the capital cost per wind turbine. So if we multiply it, then it will give us a total net present wind turbine cost. As we are calculating annualized cost to calculate the cost of energy, so we will multiply it by a capital recovery factor. So what's capital recovery factor? Actually it converts the whole price, the net present cost of any component to the annualized fraction. It means that if this is the total cost for the whole life of an wind turbine at the present situation, so what should be the annualized fraction of this cost, keeping in view the interest rates and project life? So multiplying by this component, this is just capital recovery, CRF, capital recovery factor. It will convert this net present cost into annualized cost of the component. So this is actually the cost of an wind plant capital cost per annum for 1 year. So it's annual. We have not multiplied here by CRF because it's already OM is already per year. Operation maintenance cost always per year. However, if it is for the whole life, then you have to multiply it by capital recovery factor. So here it is replacement cost. So it's the formula number of wind turbines multiplied by capital recovery factor. So actually this is this factor is used for replacement fraction 1/1 plus interest rate into raised to power component life, that's wind in our case, so it should be raised to power wind life multiplied by its replacement cost per wind turbine, and this is again a capital recovery factor. So the formulas are readily available in literature for the economics of these renewable energy systems. So here it's what's the salvage fraction. Salvage fraction is the life of any component after the project life, because the wind life here is 20 and project life is 25 years. So we have to replace this wind type life after 20 years. So just wind life is 20 and we have replace it in the second time. So the total life of a wind turbine will be 40 years, 20 plus 20. So the project life is 25 years. So the remaining 15 years price is actually the salvage price. So it will give us a 15. So how to calculate the salvage fraction? This formula is also available in the literature. So it's the size of the wind turbine multiplied by replacement cost. So it's the salvage fraction divided by total wind life. So it's 15 divided by 20. So this fraction is actually the remaining. This decides how much cost should be this wind turbine at the end of the project life. So this is the remaining life cost of a wind turbine. So multiplying it by capital recovery factor, so it will give us annualized fraction of this salvage cost. So actually this is an asset. So at the end of the project life, so it can be sold. So it should be subtracted from the wind cost. So wind OM cost, wind capital cost minus operational cost plus replacement cost. So this salvage cost always should be minus, subtracted, because at the end of the project life this is like an asset, our and above life cost of any component. Similarly, this is for solar. In the same way, the solar capital cost and solar OM is calculated. This is the number of solar size in kilowatts. This is the capital cost of the solar, and this is the capital recovery factor. So again, solar cost will be, because it's not replaced, so its life and project life are equal, so there will be no salvage and no replacement, just OM and capital cost will be there. Similarly, for inverter size, capital cost, replacement cost, OM cost, again there will be, because its life for 15 years and the project life is 25 years. So after 15 years it has to be replaced for once. So its life after project life, the remaining life will be 5 years, because its life is 15, so multiplied by 2, and the project life is 25 years. So the 5 year is the salvage fraction life of this inverter. So its salvage fraction cost should be calculated. So the total inverter cost will be the capital cost, the replacement cost, the OM cost minus salvage cost. Similarly, for grid cost, it will be what is the cost of the energy that we have sold to the grid. So this is the total sum of the grid purchases. So at which purchases at the rate of 0.08. So this is the sum of the grid purchases multiplied by per unit cost at which rate the energy is purchased from the grid. So its grid sales, how much energy is being sold to the grid at which price, at 0.06. So subtracting this one, so it will give us a net present the annualized grid cost. So how much energy is purchased from the grid? It's actually the summation in kilowatt hours, the summation of grid purchases. And how much energy is sold to the grid? That is the summation of grid sales. So what should be the annualized cost? So summation of all the component cost, that's grid, inverter, wind cost and solar cost. So it will give us an annualized cost of the system. So going toward the results, here is another file, plot statistic. Is the same file as economic analysis file in the first section, because we have to plotting. This is just used for some plotting functions till this point, and then after this point there are some just plots and some figures are and some results are displayed using this file. So let's see the results. What are the results? So let me run this one. So actually the levelized cost of energy is 0.042 starting from the. So let's see first the figures, what the figure is displaying. So in the results, starting from the reverse side, so this is the annualized cost of each component: the inverter cost, the solar cost, the wind cost, and the grid cost. The grid cost on the negative axis, because more energy is sold to the grid and less energy is purchased from the grid. So the cost will be negative. Means the grid has to pay us. This is the monthly profile comparison for each month. Let's suppose for January. Let me zoom in and out. So actually it's you can see how much energy is being generated by the solar, by wind, and how much energy is sold to the grid, how much energy is purchased from the grid, and this is the load demand. Deliberately I plotted it on the negative y-axis just to make it clear what the magnitude of this. This is just plotted on the negative y-axis to make it different from the generation sources. So as earlier said that we have much sales, our sales are more and our purchases from the grid are less. That's why our grid cost is negative. This is the ambient temperature profile for the whole year. And this is the solar irradiance profile in watt per meter square for the whole year. Whenever you see 8760 entries plot, it means that on the axis there are hours in a year, and on the y-axis whatever parameter is. So it's an annual plot, annual profile of solar irradiance. This is the wind speed at for the annual. So it's the annual power generated by the solar. So you can zoom any hour of the year. It will give us what is the profile of this solar at that specific hour. Similarly, it's the annual wind power generated from 0 to up to 8760 hours. This is the HG load annual. This is actually rescheduled HG load. You can zoom it to see how it's being the loads are switched on and off. So similarly, this is the fixed MB load that we have to meet and each and every cause for the same pattern in 24 hours. This is also the fixed load, AF load, annual profile. FF new rescheduled for the whole year. So let's see that it doesn't have a uniform profile, because how much load has to be met is totally dependent how much renewable energy is available at that specific hour. So you can see there it has some irregular, because we can turn on any load. This is actually shiftable volume load, so we can turn on at any time any device. So you will see in irregularity, a non-regular pattern in this one. So here the more loads are turned on because more solar will be available, renewable energy is available, and somewhere the less is taken. So overall in the 24 hour we have to meet the specific that load. So again it's rescheduled DU2 load, rescheduled DU1 load, and this is the comparison of all the figures of all the load demands plotted on the same figure. You can zoom it out. Even you can plot it for you can zoom it for 24 hour. And figure number 7, DU1 rescheduled for 1 week. Whenever you see there 167, it means in a week there 1767 or 168 hours. So it means that's a weekly graph. Just to zoom it out to make things visible. This just like for understanding purpose. This is also the figure 6 is also an annual load. Annual load rescheduled load demand. So after rescheduling, this load is plotted there for the whole year. You can zoom it out to see it for the specific time. This is also a weekly profile. You can see it's just for visibility purpose, some weekly plots are added there. So it's up to 167 or 168. So it's load demand, it's a wind, it's solar generation, it's grid purchases, how it's plotted. And the figure 4 is grid sales versus grid purchases. Grid sales are more and grid purchases are less. For the whole year it's plotted. And similarly figure 3 is grid sales and purchase. It's a weekly graph, just to make to make it more visible. This is also a weekly graph indicating how much is the load and how much is the renewable energy plus grid purchases. One thing is clear from this graph. You can see that the load is always under this renewable energy plus grid power. So it's below this red line, because we are just ensuring that the load has met at each and every time. When the sufficient renewable is available, then the extra energy will be sold. In other case, either load has to be met or the energy has to be taken to met this load in this off timing, like this one, because in this case the red is just above the load line in these sections. So this graph indicates that the load is met at each and every hour. This is again an comparison graph. What is the load demand, what is the wind power, what is the solar power, how much energy is being purchased from the grid. So it's here, it's an individually plotted. In the next one, we have sum all these three with respect to load demand. So let's see what results are being displayed on the command window. This is the levelized cost of energy, 0.042, and final solution is the optimal size wind turbine is 50 kilowatt, and solar cost is also how much energy in kilowatt hours is purchased from the grid and how much energy is being sold to the grid. This is actually total load demand in a year, wind energy total generated and solar energy total generated in kilowatt hours. Levelized cost of energy, average load in kilowatts, peak load, and similarly this is a load factor. Wind factor, 45% is energy from the wind, 43% is generated from the PV. For how much hours the energy is the grid is operational for a specific purpose, as you mentioned. So you have a choice either to running hours for grid purchases or for sales or for both, addition of both these. So it's totally your choice. So total net present costs. So what should amount should be spent to install this system? That should be the net at the present you need this amount to install this one. So this is the annualized cost of the system, wind cost and solar cost, grid cost, and the inverter cost.